Factors and perfect matching in journal graphs. Recap of previous lecture, we have discussed stable matching, Gale and Shafley algorithm, and faster bipartite matching, that is given by Hofcroft-Karp algorithm. Content of this lecture we will discuss factors and perfect matching in a journal graph, Tutte's one factor theorem and F factor of the graph. Factor. A factor of a graph is a spanning subgraph of G. So, K factor is a spanning K regular subgraph of G. Another definition of an odd component. An odd component of a graph is the component of odd order. So, the number of odd components of H is of the order H. Let us take an example. If let us say this is a graph having two components, then this particular component is an odd component. Why? Because it is having an odd order of this particular vertices in this component, and this particular component having two vertices, this is even. So, how many odd components are present here in this particular graph? This is the odd component which is present, that is only one. Similarly, in this particular example, see what is a one factor of a graph G. So, let us see that this particular graph which is given, we want to find out a spanning subgraph. So, this spanning subgraph will include all the vertices, that is all four vertices. If it is a one factor, that means each particular vertex should be having only degree of 1. So, if you include the degree of 1, so this will be the subgraph of G, and hence it will be called one factor. So, if you recall, this one factor is nothing but a matching in this particular graph. Similarly, another graph, let us take G2. In this particular graph, if we want to find out the three factor of this particular graph, so three factor means we want to find out a spanning subgraph. So, a spanning subgraph will include all the vertices present in the original graph, and so we are going to find out this particular spanning subgraph, which is basically a 3 regular, that is called 3 factor. So, 3 regular means all the vertices are having 3 edges out of 5. So, it can pick any 3 of them. So, 3 vertices, 3 edges are present. Similarly, this vertex will have its degree 3, will have its degree 3, and so on. So, this becomes a 3 regular. Spanning subgraph. So, 3 regular spanning subgraph of G is nothing but called as a 3 factor. Similarly, we can extend it and we can generalize it to K factor. So, when we say one factor, then we mean that we are talking about a perfect matching in the graph. Let us go and see the clarification. So, a perfect matching, that is also we are referring it to as one factor, a collection of edges such that every vertex is incident with exactly one edge. So, in this particular example, this is the perfect matching, is a collection of these particular edges, so that every vertex is incident with only one edge. So, that becomes a perfect matching, and if you take one factor, that also comes out to be the same thing. So, one factor and perfect matching are almost the same thing. The precise distinction is that one factor is spanning one regular subgraph of G, while perfect matching is the set of edges in such a subgraph. So, there are two different definitions, but they mean to the same thing. So, three regular graph that has a perfect matching decomposes it into one factor and two factor. Now, we will see the Tutte's one factor theorem. So, what is that condition in which we can find out perfect matching in the graph, whether perfect matching in the graph exists, that, or, and then we can also say that whether one factor exists in a graph, which is nothing but a perfect matching. So, this particular question can be verified using the Tutte's one factor theorem. So, some of the references also call it as a Tutte's perfect matching theorem. So, either we can call it as a one factor theorem or a perfect matching theorem, meaning thereby both these particular things are same. So, Tutte found that the necessary condition for having one factor or a perfect matching in a general graph. So, which says that if G has one factor, then for every subset of this vertex set, the number of odd components, if you remove this S subset from the graph, will have the vertices equal to that particular size of S. So, we can basically denote it by this particular condition. So, that means the number of odd components, if in G minus S, will be at most the size of S for every subset S of vertices of G. Take the example. For example, we can see this particular graph which is having a perfect matching. Let us see, this particular edge will saturate these two vertices, this particular edge of the graph will saturate these two vertices, this edge will saturate. So, one factor or perfect matching is shown by the green edges. So, this particular graph has the perfect matching. Now, let us see whether we can see through this particular condition, that is, can we prove it by the Tutte's condition. So, let us take that these two edges belong to S. This is a subset of vertices, these two vertices. So, the size of S is 2 here in this case. The remaining portion, when it is removed, this becomes one component having 4 different vertices. So, the parity of this component is even. So, how many odd components will be there in G minus S? 0. So, 0 is less than 2, hence this particular condition holds, and this condition holds, we have already seen that it has a perfect matching or a one factor. So, hence this particular necessary condition which is stated by Tutte for one factor in a graph, he has also proved it to be a sufficient condition that we are going to see the proof sketch. Now, before we go ahead, we see that an important observation. Let us say that if this is the graph and this is the set S. So, if it is removed from the graph, it will be in the form of the components. So, some components are basically having even parity, let us say the other components are having an odd parity. Now, the components having odd parity will have at least one vertices present which has an edge, and that particular edge will incident on a vertex of S in a distinct vertex. Similarly, another component which is an odd parity will also incident on a vertex of S in a distinct vertices. Similarly, here also it may have more than one also. So, at least one such component exists. So, that means one vertex from every odd component will go and will basically have an edge which will basically incident on a. So, the size of S will have these many number of components. That is why the number of odd components in after removing S will have at least that many number of or S number of elements present. Why? Because for every component there will be one element plus some more element can be there in S. So, at least that many number of. So, let us see the condition where it will violate. So, the condition where it will violate we have to see in the further examples. So, let us see that the same thing is stated over here, that if G has one factor, then we consider a set S which is a subset of the vertices of G, then every odd component of G minus S has a vertex matched to something outside it and which is nothing but that belongs to set S. Since these vertices of S must be distinct, therefore, this particular order the number of odd components of G minus S will be bounded by the number of components present in this particular S. This particular condition which is called Tutte's condition, and this particular necessary condition is also sufficient, that is being proved here in the Tutte's theorem. This particular example I have already stated. So, let us skip it and look into the proof of Tutte's theorem. So, necessary condition, we have already told you that if the graph has the one factor, that means the number of odd components will have the vertices which will go into S. So, the size of S will be at least the number of odd components. Hence, this particular necessary condition is proved. Now, let us go for looking up a more detailed sufficient condition. So, if let us say that in sufficient condition, if the number of odd component or this particular property exists, then we have to prove that it has the one factor. Now, we will prove it by contradiction. Let us see from where we, at what point we have to basically start our contradiction to prove the sufficiency condition of this particular theorem. Now, when we add an edge joining any two component, so for example, these are the components, let us say they are the odd components, and these are the components which are called even components, and this is S. Now, when we add an edge joining any two components of G minus S, so if we remove S, so they will be are distinct components. So, if we add an edge within one component of an odd parity, the parity of this particular component is not going to change if we add an edge. This particular parity is not going to change. Similarly, if we add an edge across two odd components, so odd and odd will become even. So, number of odd components will not increase. Similarly, here if two even components are basically joined by an edge, so it will become a bigger component of but even. So, in any case when an edge is added, so the number of odd components will not increase. So, that I have already explained. So, the Tutte's condition is preserved by adding of the edges. Let us assume that an edge E is added sufficiently into the graph and we obtain a G prime graph, then that particular condition, that is the odd vertices in the new graph G minus S, will be having that particular same value, that is the number of odd components is basically this particular equation or this particular property is not affected. So, that is basically sure. So, if we add an edge and we see that if particular graph G prime has no factor, then the original graph also has no factor. That means, the addition of the edges into a particular graph, it will not basically make that graph a perfect matching. Therefore, this particular theorem holds unless there exists a simple graph G such that G satisfies Tutte's condition. Now, G has no one factor and adding any missing edge in G will yield a graph a one factor. So, let G be such a graph and we obtain a contradiction by showing that G actually does contain one factor. So, what we are going to prove in the sufficiency condition is that if a graph is given G and if we add sufficient number of edges, we form a G prime, a new graph. So, if G prime do not have the one factor, then by adding this particular edge into G, so G also should not have the one factor that we have seen, but we differ from here and this will be our contradiction. So, our contradiction will assume that in the graph G, if we add an edge, we will make another graph G prime and this we will show that we will assume that this particular G prime will have the one factor, and the contradiction to this contradiction contradicting this particular statement will prove that the sufficiency condition and hence this particular graph satisfying this particular property will have one factor. That is what we are going to prove. So, let us prove that by adding this particular edge, the graph original graph G is not having the one factor and thus it is going to do the contradiction. So, case 1. So, let us assume that U be a set of vertices in graph G that have the degree n minus 1. That means, in a graph we will find out. Let us take this particular example of a graph. This particular graph has two vertices, this particular vertex 1 and vertex 2, its degree is n minus 1. That means, total value of n is 4. So, 3 are present here, 3 are present here. So, it is basically n minus 1 and this is also n minus 1. So, we are collecting up such vertices and let call it as U. So, this also will be part of U, these vertices will be part of U, other vertices are not in a part of U. So, let us see the case 1. The vertices in each component of G minus U. So, if we remove U from the G, we will have this set of vertices. So, the vertices in each component of G minus U can be paired in any way with one extra in the odd component. meaning to say that when we remove u from the graph, it will be in the different components. The components having the odd parity, we will find out a vertex and try to match a particular vertex in u, that we have earlier also stated. The leftover vertices of u here, the leftover vertices, for example, every other vertex of u will be having a matching in that odd component. This is even component, so there is no such vertex present here in u. Now, the vertices which are left over in u, that means the number of odd components is always less than s, here we call it as u. Since the number of components are more, that means the number of odd vertices it will match, and then the remaining ones, it is talking about the remaining ones, the difference, and they can be paired with each other. So, the remaining vertices are in u, which is a clique. So, you see that is why these cliques are there. So, if it is 2 vertices, then there will be a 1 factor. To complete 1 factor, we need only show that an even number of vertices remains in u. So, these set of vertices which remains is basically an even number. So, even number can be included in the 1 factor. So, we have matched an even number. So, it suffices to show that Ng is even. This follows by invoking the Tutte's condition for S is equal to empty, since the graph of odd order would have the component of odd order. Now, let us see the case when G minus u is not the distinct union of cliques. So, the previous condition says that G minus u is a distinct complete graph, that is the cliques, and we have done this particular one perfect matching. Now, if these distinct vertices in u, G minus u is not disjoint union of, so what will happen then in that case? So, in case 2, in this case G minus u has the 2 vertices. So, G minus u, so this is u, and so this becomes G minus u, these are the components, has 2 vertices at a distance 2. These are non-adjacent vertices x and z, and a common neighbor y, and y is not in u. So, if it is not in u, then it must be in some component. So, g and x and z, they are not basically having a direct edge, and they are connected through, let us say they have a common neighbor y, and this y is not in u. Furthermore, G minus u has another vertex w not adjacent to y, since y is not in u. So, we now are getting x, z which is not directly connected, y is there and w is also there. So, y is not in u, outside u. Now, by the choice of g, adding an edge to g will create a 1 factor. Let m1 and m2 be the 1 factor of g plus x z. So, x z, they are not directly connected. So, we hypothetically we are placing an edge and we call it as x z. Since x and z they are not directly connected, so we are placing a hypothetical edge, imaginary edge. Similarly, we are also adding y w, this also a hypothetical edge we are adding up. These two edges we have added. So, which is shown over here, let us say this edge is hypothetically added and this edge is hypothetically added into G. So, it suffices to show that M1 is a matching, M1 is one factor and M2 is one factor. Union these two edges will contain one factor and we can avoid x, z and y, w, because this will be one factor in the G. So, let us see when we take the symmetric difference of two matchings or symmetric difference of two one factor, you know that it will become a graph with a vertex degrees either 0 or 2, 2 means it is a cycle. So, this particular cycle M1 followed by M2, M1 followed by M2 followed by M1 followed by M2, M1, M2, M1 and M2. So, this becomes basically a cycle. Now, the question is, we have added these two hypothetical edges. Now, if we can show that this particular cycle still we can get without these edges, then this cycle will be the sufficient to show that it is having the one factor in the graph. So, let us assume that we can still get a cycle, that means if we start from somehow reach to y and y if we reach to z, from z to y and then we can take around, and when we reach to x we can come back again and take around and so on. So, either we can avoid x z or we can avoid y w in this particular way. So, when we reach x, then basically we can reach to z also and so on. So, in this way we have obtained a cycle without even these hypothetical edges that we are going to see. So, here we have shown that we have produced a one factor of this particular cycle C, including x, y and y z, that does not use x z or y w. So, combined with M1 and M2 outside this particular cycle, we have one factor, we have obtained a one factor and we are using these edges, but we are not using these two edges. So, still we can complete a cycle. So, let me again state this. If C contains, C means the cycle, if cycle contains both y w and x z as shown below, it is containing at this particular present, then to avoid them we use y x or y z, any of these two. So, in the portion of the C starting from y along y w, we use the edges of M1 to avoid y w. When we reach x z at this end, when we reach x z we use z y to arrive at z as shown, otherwise we can use x y. So, in the remainder of that particular cycle C, we use the edges of M2. So, we have produced, that means if we look this part, so if we are removing M2, then basically we are basically using this particular edge, and if we are removing M1, then we are using this edge. Still we can complete the cycle without them. So, we have produced a one factor of C plus x y plus y z that does not use x z or y w. So, instead of x z and y w, we are using x y and y z. So, combined with M1 and M2 outside, we can achieve the one factor of a particular graph. So, that means by adding an edge, if the original graph does not contain one factor, but we have reached to a contradiction which is shown that it is having one factor, thereby we are contradicting the original hypothesis. This contradiction of a contradiction will prove that the sufficiency condition is satisfied of the Tutte's condition. Remarks: like other characterization algorithms, this algorithm will yield the short verification both when the property holds and when it does not. So, we have shown when the property holds, there exists a one factor. We will show when the property does not hold, still that particular characterization is valid. We prove that G has one factor by exhibiting 1. When it does not, then we have to find out a subset of S that if we remove, it will leave too many odd components. Hence, it will violate the Tutte's condition, and hence we can state that the graph does not have one factor. Furthermore, for any graph G, if we take a subset S of vertices and counting the vertices modulo 2, will show that the cardinality of S plus the number of odd component has the same parity as n. If we take the difference, then also it has the same parity as n. So, we conclude that if n is even and G has no one factor, then the number of odd components exceed by S, odd component exceeds S by at least 2 for some S. So, in this way, if there is no one factor, then we can also estimate about the size of the maximum matching by taking this particular difference. So, again we are going to give another definition of a join of two simple graphs G and H, which is written as G join H is the graph which is obtained by the disjoint union of G plus H by adding the edges to both edges x y, such that x belongs to a particular vertex in G and y belongs to particular vertex in H. So, for all such vertices of G, there will be an edge to the vertices of H. Similarly, for every vertex of H will have an edge to the vertices of G. So, that gives. So, let us take this particular example. So, if we are given K3 and another graph is given P4, so K3 join P4 will look like this. This particular vertex will have the edge to all other vertices, this also will have the vertices to all other vertices, this also has the same thing, and this basically will result into this particular graph, that is the join of two simple graph is a graph that is shown over here. Now, there is a corollary given by Burge-Tutte formula. So, that corollary says that the largest number of vertices saturated by a matching in G is the minimum of the subsets of vertices such that n minus ds, where ds is the number of odd components in G minus S minus the cardinality of S itself, that I have earlier explained, but let us take an example and show that. So, you know that this particular graph is not having the perfect matching. So, we have to find out the largest number of vertices which can be saturated by a matching in G. So, we are going to take S, let us say this is S. So, the cardinality of S is 2 and the number of odd component, this is 1. So, the ds, if we compute, this will be 2 minus 1 and 1, and if we plug in this particular ds value, so the total number of vertices is 5, 5 minus 1, this comes out to be 4. That means 4 is basically the number of vertices which are the large, this is the largest in size which can be saturated by any given matching. Let us see. Since this particular graph is not having one factor, so we have to find out that particular matching which will saturate the largest number of vertices. This is vertex number 1, 2, 3 and 4, and here using this particular formula also we have computed that 4 vertices, this is the largest value of these vertices, are being saturated by the matching. So, this particular formula can be utilized. If the graph does not have one factor, then it can identify how many, what is basically the maximum or the largest number of vertices which can be saturated by the matching. Now, there is another corollary which says that every 3 regular graph with no cut edge has one factor. So, let us take this particular graph. So, this particular graph is a 3 regular graph. 3 regular means every vertex or every node has the degree 3. Now, this particular graph is not having any cut edge. So, that means if you remove this edge, the entire graph is having one component. So, there is no cut edge present. So, this particular graph has a matching, a one factor, and this particular one factor is shown over here. This is one such matching, this particular edge will have another matching, this edge will have another matching, and this particular matching. So, this particular graph has one factor. Now, another important graph is called a Peterson graph. So, Peterson graph is also 3 regular graph, that means all the vertices having the degree 3. This also has a one factor. So, if we include these edges as a part of the matching, then you can see all the vertices of this particular graph is saturated, and this condition is called perfect matching or a one factor. So, this is a 3 regular graph, and this is a important, the name of this graph is Peterson graph. So, Peterson graph has a one factor. Now, then there is a theorem which says that every regular graph with positive even degrees has 2 factor. So, let us consider this pentagon K5, it is also called. So, this is a regular graph with a positive even degrees. So, the degree is 1, 2, 3, 4. So, all the vertices are having degree 4, it is a 4 regular graph. Now, this 4 regular graph has the 2 factor. What is 2 factor? 2 factor is a spanning subgraph with the degrees equal to 2. So, let us see in this particular already shown about the 2 factor. So, let us start from vertex number 1, we can reach vertex number 2, from 2 we can reach to 5, from 5 we can reach to 4, from 4 we can reach to 3, from 3 we can reach to 1. Similarly, we can also identify this is 2 factor, another 2 factor also we can identify. Let us begin from we can reach to 2, we can reach to 4, we can reach to 1, we can reach to 5, we can reach to 3 back again. So, this is another 2 factor. So, this particular graph has 2 disjoint 2 factors. Present in the graph. So, it has also 1 factor. So, that means 1 factor plus 2 factors also you can identify, and that is shown here in this particular graph. So, again I am repeating the theorem that every regular graph with positive even degrees has 2 factor. Now, let us see the definition of f factor. Given a function f which maps from vertices to a number n, which also includes 0 besides natural numbers, and f factor of a graph is a spanning subgraph H such that the degree of the vertices is basically f, fb for all vertices, and f is a number which is called f factor of a graph. So, Tutte proved a necessary and sufficient condition for a graph to have f factor. He later reduced the problem to checking for 1 factor in a related simple graph. Conclusion: in this lecture we have discussed factors and perfect matching in a general graph, Tutte's 1 factor theorem and f factor of a graph. In upcoming lectures we will discuss the matching in a general graph, which is given by Edmonds Blossom algorithm. Thank you.